Hola. Good afternoon. We will start the second part of today. So for our first presentation is Xiomara Marquez from National University of Costa Rica, in National University.
Good afternoon. My name is Xiomara. I work in Universidad Nacional in Heredia. I work in a group of oceanography, mostly physical and biological oceanography. And my work is estimation of eddy viscosity coefficient in Bahía Santa Elena. Bahía Santa Elena is this channel, and this channel has a width of 2 kilometers, and this is the part of interest of this research. Santa Elena Bay is located in the North Pacific coast of Costa Rica. In this region is this small hole here. This region is influenced very strongly by winds because of the gaps between the chain of mountains. The gaps produces wind jets that influence all the north part of the Pacific coast of Costa Rica. This territory is dedicated to the conservation of the ecosystems. Only tourism and resource extraction are developed in this area. And it was declared a marine conservation area, and it's very important for the conservation of the species. The Bahía Santa Elena is considered like an estuary. What is an estuary? An estuary is a semi-closed coastal water body, and the principal feature is that there is an exchange of fresh water from precipitation or rivers with salt water from the sea, due to differences in density, tides, and winds. Also, estuaries come in all shapes and sizes, and also have other names like bays, lagoons, fjords, inlets, or channels. The classification of the estuaries depend on the topography of the basin, the salinity, or even to the circulation. An estuary can be classified as a positive estuary or a negative estuary. In a positive estuary, we have here the estuary, and this side is the sea, and then the fresh waters goes to the sea, towards the sea at the surface, and the seawater enters to the estuary at the bottom, because the salty water is denser than fresh water. In an inverse estuary, the circulation is the opposite. In these estuaries do not have much fresh water supply from the river, or this estuary can be located in places with high evaporation rates, and the salinity of the estuary increases in this place, and this water sinks. Then the water from the estuary goes to the ocean at the bottom of the estuary, and the water from the ocean enters at the surface. This is the opposite. This is very important when we are talking about pollution, because inverse estuary seems to have to last more time to clear the waters. In this research, we use a mathematical model to try to reproduce the velocities of the water in this estuary. This mathematical model was proposed by Kasai, and it was used also for Valle Levinson to study some estuaries in the Central America region. We have our topic is mainly physical oceanography. We use equations and try to reproduce circulation patterns. In this model, we say this the x direction, the coordinate x is this direction along the channel. The y direction is this direction across the channel, and the z direction is up and down, and z is related to the depth of the channel. In this case, this u represents the velocity enter or goes out from the channel, and v represents the velocity of the fluid in this direction, the y direction, across the channel. These two equations comprehend the Coriolis force. The Coriolis force is the force that the rotation of the Earth influence some fluids, making these fluids moving to the west. This term and this term. This term here are pressure gradients due to salinity or due to other causes. And this term here is a term of viscosity. The viscosity is related to the wind or another process. In this model, we define this n function, which is a gradient or a change on this variable eta. Eta is the height of the level of the sea respect to an average level. And this parameter d is like a gradient or change in density along x or along y. This g is the acceleration of the gravity, and rho naught is the density of the ocean. And then we have these equations. The main goal of this research is try to estimate this parameter, which is called eddy viscosity coefficient. This AZ coefficient hasn't been measurement or calculated for many places in Costa Rica. We don't know how much is this value. We try to make an estimation because it's important to models to try to predict some behavior. And this viscosity coefficient is also related with the wind, with the effect of the wind. If it's very large, the wind is very important, but if it's very low, it's not important, or the viscosity effects are not important in this channel. We have also the Ekman number. The Ekman number is the ratio between eddy viscosity coefficient and the Coriolis force related to the rotation of the Earth. F is the Coriolis parameter, which has this value for Costa Rica, and the maximum depth of the channel is 20 meters. The Ekman number is a ratio between these forces, the wind and the Coriolis force. If we calculate this number, we can decide which force is more important for the behavior of the estuary, if the wind or the rotation of the Earth. And then we try to solve this system of equation, but it has analytical solutions. We define a new variable, W. W is the u velocity plus the velocity across the channel, and we define W through these two functions, F1 and F2, which are related to the depth of the channel and the maximum height, and also this parameter alpha. Alpha parameter is, this E means complex number, which is certain kind of numbers which separates the velocities in X and the velocities in Y, in this case. It's related alpha also with the eddy viscosity coefficient and also with the Coriolis parameter here. And these two functions we use to calculate W, and with W we calculate U and V. But we introduce certain parameters or numbers like random numbers, but we try to find the right numbers to put here. The D parameter, the gradient intensity, also the N parameter, and the AZ parameter. For the N parameter or the gradient in the height, we use this function depending on Y and depending on this number K, which we set like 0.063. This number is called Kelvin number, which is which has a relation with the strength of the rotation of the Earth, how much important is for this basin. Then we have a very small Kelvin number, which means the rotation is not really important in this channel. And then the parameter D is this value we take like an average from measurements. These are the observations. We have here velocities. The velocities in the channel enter and going out the channel are between 5 and 10 centimeters per second. And we found that at the bottom, in these two surveys, we find two regions in yellow color, which means water goes towards the ocean at the bottom, like in an inverse estuary. Then we believe that this inverse estuary, this inverse behavior is very common in this region in the months of August and October. After we did some calculation, we tried to set the parameters and try to adjust the parameters to try to reproduce this pattern of velocities. And the best trial is this square here, with a number of the eddy viscosity coefficient of 2.3 10 to the minus 3 square meters per second, and related to the Ekman number of 0.23, which means that between the wind and the Coriolis force is stronger than the wind in this channel, but there is no much difference. We also make a calculation of this parameter at the surface with other formula which only involves a gradient in the velocity, the air density, the ocean density, drag coefficient, and also the wind velocity. And then we find this number at the surface of 4, 10 to the minus 3 square meters per second, and which is very similar to the previous result. Then we found this coefficient, and this corresponds to a stratified fluid. Here there is a mistake. A stratified fluid. There is the presence of layers, and these Ekman numbers, very less than 1 means the Coriolis force is more important than the wind in the channel, and at the moment this is the state of our results. Thank you very much for the opportunity. Questions?
Thank you so much, Xiomara. So we have time for questions.
Thank you for your presentation. I wanted to ask you, what about, so what kind of, let's say, monitoring instrument do you have on the estuary for, let's say, currents, measurements, this kind of stuff?
The other colleagues of the group, they measure along the transect several times. They go in a boat measuring the velocities with this instrument around a complete cycle of tide. During 12 testing hours, they measurement with an ADCP instrument.
Thank you for your presentation, Xiomara. I was wondering, which are the implication of this seasonal change that you see in the viscosity?
We really don't find like a seasonal change because we just measure during August and October, which is the same season, and we don't have yet new data to measure another time of the year, but we really like to have like a order of magnitude of how much this value is, because we didn't measure before, nobody measured before in any estuary in Costa Rica, and then we just try to estimate a number. You're welcome.
More questions? Thank you.
Thank you.
So our next presentation is Patricia Eichler. So we'll be online.
Hear me?
Volume is. Hello, Patricia. Yeah.
Hello, can you guys hear me?
Yes.
Okay, good. It's a pleasure for me and an honor. I wish I was there with you guys, but my flight got canceled, unfortunately. And I spent 22 hours in São Paulo airport trying to get there and be with you, all you guys, but unfortunately, I am not. So here I'm stuck in São Paulo. But okay, I'm gonna share my presentation. You guys see if it's, can you see okay? Slideshow now? Okay, good. So Thank you for the invitation. And today I'm going to talk about the data we collect in 2016 on board of the JOIDS resolution, the IODP vessel, the International Ocean Discovery Program. And I have to thank Professor Helenice Vital for this opportunity from the Rio Grande do Norte Federal University, and also the Geodynamics and Geophysics post-graduation program, and of course the CAPES and CNPq, which we do our research. So today I'm going to talk about the explosive volcanism periodicity past cycles record within the last 800,000 years, like 0.8 million years ago, evidenced by tephra and benthic foraminifera. I think I can take this. Yes. Okay. So this is the study area. It's the Ring of Fire over here. So we got a lot of volcanic activities. So this is New Guinea, Papua New Guinea. It's the north of Australia. So we collect nine cores, but I'm going to talk about this U1485 that we collect very close to the shore, kinda. I thought about the JOIDS resolution, the ship that it's equipped to collect the cores. So the site was close to shore, but however, it's 1,145 meters deep. And so the ship stays here and it doesn't move, right? They have buoys to make it to not move. So the drill pipe goes all the way and 1,000 meter high, deep, and then the drill bit goes and get the samples, right? So this is a scheme for you guys to understand where the samples came from. There was the expedition 363 from Western Pacific Whirlpool. So it's actually the warmest place in the Pacific. So here we have the introduction. I have this evolution of the temperature from the planet Earth until 2100. So we are 2023, 24, right? Happy New Year for everyone. So we have this detail for the last 5.5 million years ago, and we were able to see this. There was the 41,000 cycle and the 100 cycles here. But here, it's very important to mention that's the 1,000 years before present. And it's interesting because we can see here that 2050 is very close, and it's almost 4 degrees Celsius over there. And they're projecting that 2100, we're going to have almost 9 degrees Celsius. So it is a problem that we got to face because how were you able to see that? So by looking at the last glacial and interglacial cycles by the MIS, the marine isotope oxygen stages, we can see that this MS2 is the coldest, driest period, and all the odd numbers, they are droughts in the oxygen, and the even numbers have high and they are cold periods. So by looking at the marine isotope oxygen, we were able to see this interglacial and glacial periods. And this is something that's a lot of research that has done that, and so we are able to see this. But I'm gonna tell you about our results and how we fit in this description, right? So here is pictures of our 1485 core, and here is the present of tephra layers and ash mixed with silt and clay, and indicates the sedimentation is it's pyroclastic through the entire site. So what happened is when they collect the core, we didn't know what it was. So when I was looking at the samples, looking at I'm a micropaleontologist, I was looking at the foraminifera, I'm going to show you later, but I saw in my samples these little fractions and I didn't know what it was. So on board, they brought this volcanic expert and he said that was tephra. So based on this observations, we were into this volcanic sites. And this 1485, it's a very important one to show what was happening in the last 800,000 years ago. So we saw there was accumulation of hemipelagic clay and biogenic components is interspersed with more rapidly deposited coarser grain and sand and silt. And the shelf sediment was fluvial and it was carried by a mass gravity flow. That was what we were able to tackle at the ship. That was Yair Rosenthal that was able to describe, because there was, and then they realized that the possible triggering mechanism that could be doing this, the mass flow deposit, that could include the earthquakes and tsunamis, and of course the shelf slope sediment stability during times of rapid deposition, such as what we can occur during some Eden River flooding events. So in our samples, we were able to detect that there was presence of volcanic ash, specifically on the 34, 35, and 36, and 39 intervals. So, and then we were able to pinpoint the change in the fauna, at least after some volcanic episode that I'm going to show you. So, but before show you the results, I'm going to explain a little bit about how we do the markers. So the planktonic foraminifera give the ages, right? So the sample one we found was a typical diverse open ocean tropical assemblage. And the samples 1 to 4, they were assigned about Globigerinites ruber. And the Globorotalia flexuosa. So these markers, the presence of them can give us specifically the date. And I'm going to show you in the graph later. But so the presence and the absence of them indicates, like, for example, the presence of this one indicates that is at 0.07 million years ago. And the Globigerina ruber, it was 0.2, so it's a little old. So we're going down to the core, and we see that Globigerina callida and the base of flexuosa are very difficult because of the rarity of the markers. When we go down to the later years, the shells are going to be a little dissolved, so it's getting difficult to observe what the species are. But however, we were able to tackle until the end, and we recognize all the bio horizons for the planktonic markers. So the bottom was done with this subzone of the Globorotalia tossaensis, and there was the marker. So, and they confirm about the Pulinatina populations that have a strong dextral dominance through the entire whole. So the entire section lies about the L1 sinister excursion. So all our samples were all younger than 0.8 million years ago. That's why we were able to tell the age. It was by looking at the samples at the ship. So what we were able to see is that by looking at the planktonic, we look at the marks, and there was this last maximum glaciation, 1 to 4, this part, and then 8 to 9, we have the early Holocene, and 15 to 16, something that we record the late Pleistocene, and 44 and younger, they were younger than the middle Pleistocene transition. So our samples are this. So I'm gonna go a little in detail on this graphic, but just before I move, this is what our Earth looked like in the glacial time. So, so just by putting this on detail over here. So this is the benthic foraminifera diversity along the biozones that we describe by the planktonic. So planktonic gives you the age, and benthic foraminifera gives you the environment. So what was it is just the diversity of the benthic. It was very decreased after some events, and we didn't know precisely what, but specifically here, we were able to see there was ashes here and here. So we were able to take this diversity decrease in this benthic after this Pleistocene volcanic eruptions that occur in this area and at this time. So this decrease in the benthic diversity after this Pleistocene volcanic eruptions recorded after the presence of volcanic ashes and tephra. So that's the intervals that we were able to observe the presence of the pyroclastic elements. And after this, we see a decrease in the pattern of the fauna. So here we also put one organism, the increase in Ovidgerina proboscidea is our worm species. So there's the curve of the worm species that we were able to see by the benthics, and here we have the average of Ovidgerina proboscidea. And we can see that the increase in this population and the abundance of warm water species indicate close relationship between climate warm and nutrient delivery via freshwater discharge through the Sepik River. So that's what we were able to tackle by looking at one species and looking at all the benthic, the warm species, because it's a pool of species that we select that they were already discussed, that were warm species. So just to show you a little bit about the benthic foraminifera, how we were able to define is the change in diversity shows balance then of alternative deep, cold, and shallow, that's warm benthic foraminifera along the past. So the deep water fauna is dominated by cibicidoids pachyderma. It's an upper bathyal species from the early Oligocene through the Pleistocene. The Ovidgerina hispida from this one, from the early Miocene and through the Pleistocene. And this is the Ovidgerina proboscidea that is from late Oligocene through the Pleistocene. And they're all both bathyal, these two. And also, Ovidgerina mediterranea, with the name, we already noticed that is a warm species. So this is an alterneritic upper bathyal form characteristic of warm waters and high salinities, little dissolved oxygen, and very high levels of organic matter. So this is the fauna we got in this core. Also, Boliviana quadrilatera, this organism over here, that she is a deep from 200, 500 meter deep, and Bolivina robusta. She is from 3 to 900 meters, and Rhotalinoides compressisculus. It's a shallow water worm species that it occurs from 2 to 37. So if it occurs from 2 to 37 meter deep, how that was at 1,000 meter? So that was because we talked about the massive slide that actually transport the species along the core intervals. And they all showed higher diversity peak. That's probably an interglacial cycle, right? So if you have a warm species, so probably it's oops. So we found 5 decreasing diversities that respond, so that the benthic community respond to. So we are explaining that this diversity is because of the climate that they had to face. So the response was an ecological change in the pattern. So this change will take a whole community and the entire ecosystem to extinction, since we've seen like 5 in what I show you. So are we going to face another one? Is perhaps the 6th mass extinction coming? Like we were discussing, 2050 or 2100. Do you think we're gonna make geological history? Unfortunately, I think we're facing the Anthropocenic 6th extinction. I put a list this question marks because even though my data and data from lots of research I know, they actually go again with mine, and we can see that 2050 probably we'll be facing an extinction. That's a horrible thing to say, but it is kind of true because we are facing some warming that goes back to the Pliocene. And the Pliocene is the warmest time on Earth. So just go back now for the conclusions. So our results, they support our potential of benthic foraminifer as a qualitative tracer of water mass temperatures and the nutrient content, and should apply on high resolution. And we can also get at least 3 indicator species. And the diversity decrease that shows inverse correlation by benthic foraminifer to high presence of ashes and tephra in the past. The chronic explosive volcanic activity that was generated in stable benthic habitat, it was colonized by only a few species. So the increase in atmospheric CO2 concentration leads to decreased pH and carbonate availability in the ocean. So we're already talking about this, the ocean acidification and the ability of marine invertebrates to tolerate the acidity are actually the windows into the future to study. So by looking at the past, we can say what was going to do, what is going to happen, right? So, and none of the previous extinction were as severe as the ecological or even taxonomic extinction in the areas that there is shallow carbonate that we were predicting because of the rating of increasing the CO2. And unfortunately, we expect that the increase in the temperature in the Holocene and the tendency until 2100 will take us to the warmest Pliocene climate, with the unfortunate consequences of living in a warmer than optimum world. Our research suggests that we're fast approaching this disastrous effect of the 6th Anthropocene extinction. However, we can successfully surmount the challenges of the biodiversity loss and climate change and dramatically alter their trajectory if we can pinpoint and remediate problems with the near future. We know that as average temperatures rise and the frequency of extremely warm years increase and the impacts of habit loss and fragmentation become even more increasingly apparent. We are with no doubt entering a systematic extinction, even because of the rapid decline in biodiversity. The majority of these species inhabit environmentally delicate tropical and subtropical areas susceptible to human impacts. This refers to a situation where the extinction of one species impacts other species that rely on it for survival. So, also placing them in a domino effect, risk of extinction as part of a destruction chain of reaction. Because if we destroy our first and second consumers, we will decrease the biodiversity of the top predators. So what do we have to do? So the direction is stop cutting and burn forests. Okay, you can't just plant trees. It's not the solution. We have to preserve forests that allow the top predators to be able to actually going into the area and be able to propagate, disseminate biodiversity. We need to stop global on the trade of wild species. We have to stop contaminating the ocean. We need to preserve the whales. Whales are the carbon sink. So all the big animals, including whales and top predators, they have in their own bodies the carbon. So if the animal is alive, it's captured in the body. So when they die, that's when it goes to the atmosphere, and that increases our global warming. So we need to keep continuing study areas to be able to conserve and preserve our biodiversity. Okay, and conservation is very different than preservation. Conservation is when you conserve an area, you are able to get out from it. But preservation, when you just need to leave the forest and the ocean the way it is, and nobody can explore anything, even if there is something a study directed. At this point, preservation is what we need. So, and just to finish, a little advertising of the book that was from 2020, a little bit during the pandemic. So that's the first time I'm able to give like this basic from for ecology. There's 10 chapters, and this one, climatology and benthic fauna extinction, is the one that I just presented for you, and I hope you guys are interested enough to take a look at the book. And that's what I had to talk today. And thank you. And even though we have a global warming, I still love the sun. Thank you.
Thank you, Patricia. So we have time just for one quick question. Okay. So no questions. So thank you so much, Patricia.
Thank you.
Our next presentation will be Alessandra Savini from University di Milano Bicocca. Alessandra Savini is an associate professor at the University of Milano Bicocca. Her research interest includes research methods in seafloor imaging and mapping and geomorphology of continental margins. She investigates the interaction between submarine geomorphic processes and benthic organisms to decipher the response of submarine landscape and landforms to Pleistocene and Holocene climate changes. She's also a member of the scientific committee of the Mare Center, located in Maldives, where she coordinates the annual training course of mapping technologies in coral reef environment. So welcome, Alessandra.
Hi, can you hear me?
Yes.
Okay, thank you. So thank you so much for inviting me. And sorry to not be there, but I had some family issue. I couldn't plan to reach you in Costa Rica. It would be wonderful, but unfortunately I couldn't. So again, thank you. What I'm going to present, maybe I have to go in presentation mode, sorry. Okay, can you see the presentation? Okay, so my presentation will deal mostly on some technical aspect, more than sediments and data as we saw before. But what I would like at the end is to stress out that actually to collect this kind of geospatial data set is really strategic to plan the sampling and the observation and the kind of data we have to collect to explain the evolution of a kind of environment. We are going to talk about reef landforms and landscape, and they are belonging to, they basically are perceived as a coastal landform. And so the first thing that I would like to mention at the beginning is how you have to collect data on a coastal zone in order to provide a geomorphological map. Then we will have a look into not the knowledge, all the knowledge, but some basic topic related to our knowledge on coral reef landforms and landscape, and the poor knowledge we have regarding the mesophotic reefscape in particular in terms of the geomorphology of the mesophotic zone. And then we will show, I will go to show you some data collected in the Maldives. So I have to move just a bit because otherwise I cannot see very well my presentation. Okay. If you want to collect or to provide a geomorphological map in a coastal region, you have to employ the kind of range of technique because you are going to survey the land system and the marine system. And one of the most challenging things to do is especially collect data in the near shore, because we know that with the use of the satellites, we can have very nice data and accurate data collected on land. With the use of acoustic system and using research vessel, we can now explore also the deep environment, but the near shore is something that is a little bit challenging because you have to, the satellite cannot penetrate the line. Now there are some progress as we will see, but still there are many situations in the coast, in the near shore. For example, if you are going to survey beach systems, such as in this case, turbidity or water movement can really obstacle the collection of nice optical data or accurate optical data. But today we are going to see what is happening in the coral reef system. So let's see this profile of a general schematic profile of a coral reef system. This is a section of, could be a section of a very simple section of a barrier reef or a atoll reef. And we know in general that with satellite, we really collected a huge data set that were able to actually provide nice map that show the global distribution of coral reef around the world, because the main part of coral reefs is shallow, or at least is the one that we know better. And because of that, because we can survey the Earth with satellites, and the shallow region can be really easily mapped with satellite. Obviously, you have to calibrate the data, so you need to collect in situ data to calibrate the data you are going to collect with the sensor. But as I was saying before, today we have a very nice map that are showing the distribution of coral reef all around the world. What we have to note, however, is that with satellite, especially until some years ago, the resolution was not so high, and so yes, we can map them at a global scale. But if we want to map that in detail, now we have to adopt new technology, and we have to collect higher resolution data than the one provided by satellite. Even if, as I was saying before. Now there are sensors that can reach a meter of resolution. So many scientists are using them. I here cited the Allen Coral Atlas because it's a nice web platform in which you can actually explore all the reef, and the data are also represented with kind of high resolution. In addition to this data, there are also interpretation of the geomorphology of the reef, but still, as I was saying before, for the shallow part. Another advantage of using satellite, a very important advantage, was the point that scientists developed a range of techniques to classify this data. And this is something that triggered or that fostered a big scientific community in being, with time, more accurate and more precise with their classification. They developed image processing techniques and supervised and unsupervised classification technique, really advanced. And also they developed a sort of different classification approach. We do not have the time here to go deep in this topic, but actually classifying landforms is something that is not easy, and you have to provide names that are accessible by a huge community and not only from people that have expertise in that. And so really is there is also a wide many scientists that are working in order to provide proper classification terminology and approaches in order to provide accessible map that can be used to manage our ecosystem in this case. I here just mentioned some of the algorithms that have been developed. Some we will have a look at some of them with the data that we collected. But I was impressed by one paper that has been published in 2021 because it was the first one actually that really provide a synoptic view of the approach that you should be employ to map coral reef landforms and landscapes. And as you can see from the scheme that has been provided in the paper, they integrated multi-source data. They also integrated, for example, wave modeling and other information in order to provide the geomorphological map with the terminology that can be used by a wide community. The final goal was to provide maps and global maps for the management of this system. But as you can see from the picture, the authors recognize the importance of, as I was saying, using multi-source data and the range of technology if you want to have really a synoptic view and all the information related to this environment. So they were the first one that cited the importance that actually they were not the first one that collected this kind of data, but they provided this picture in which they recognized the importance of collecting also bathymetry, because I have to say that the first data collected in the deeper part of coral reef system started to appear in the literature very recently, and still we have very few data regarding the deeper part collected with the acoustic system. But I hope that we will you will have the appreciation at the end that they can be very useful to understand the recent evolution of this particular landforms. So go back to our general scheme. Now we are going to see what we can do with a multi-beam system. With the multi-beam system, we can actually map the deeper areas and obtain a coverage or elevation data that can be at quite good resolution. Depending on the depth, you can reach a resolution of a few meters or even less than a meter, or some meter if you are going deep. The problem is that when you are going to acquire data with the multi-beam system, with the acoustic system, you are not using electromagnetic waves. So the answer is actually an elevation model. You cannot appreciate the nature of the seafloor. So it is very critical to explore further the seafloor from which you have you obtained the 3D model in order to understand the true nature of the seafloor. So generally, scientists working at sea are using ROV, as we know. And with the ROV, you can even go closer to the seafloor in deep environment and collect high-resolution bathymetry. You can also use autonomous underwater vehicles that are That is something,
Alessandra, sorry.
yes?
Sorry, we lost the one last minute of your talk.
Oh,
Yes. Yeah, just this slide.
okay.
No, the
I guess
last,
it's
the
not.
ROV, the ROV. Yeah, from the
Okay.
ROV.
I was
yeah.
just mentioning that you can use a range of platform to collect multi-beam data from the vessel to the ROV to the underwater, to the autonomous underwater vehicles in order to get a closer survey to the seafloor and so improve also the resolution of the model. I don't know if you catch the point that was the most important message, was that the multi-beam data are representing a model. You do not have the visible perception of the seafloor. You do not know the nature of the seafloor. So you have to explore then the seafloor with cameras, with underwater cameras, or you have to collect samples. But actually the model helps you a lot to understand which are the sites in which you have to collect samples in order to have a general perception of the underwater landscape. So, and then still talking about the shallower part. We mentioned it before, the satellite, but recently there is a new methodology that is extensively applied to coral reef environment in order to collect the data in the near shore with a higher resolution than the one provided by satellite. Because actually, even if satellite now can reach a resolution of a meter, some images are also free. You can download them from internet. They cannot actually detect important changes or short temporal changes in the environment, and especially in the shallow reef environment that has been considered the more active part of the coral reef system. So now people are employing LiDAR technology using drones, aerial unmanned vehicles, or they collect imagery, RGB imagery that can visualize with high detail the area. I forgot before to mention that obviously the multi-beam can also survey you can turn the multi-beam toward the area that you want to see, to survey. The important thing is that the multi-beam must be in the water, no? So you can actually join the data collected with LiDAR or autonomous aerial unmanned vehicle and join them to the multi-beam in order to have a seamless model. This was our goal when we started to deal with this environment, actually. And so, why I did this introduction? Because I want just to stress that actually the deeper environment in coral reef system is truly less explored. We can refer that to, we can indicate the deeper environment as the mesophotic reefscape. In general, in literature, it is indicated as the area that range from 30 to 150 meters. Even if with satellite and drones, you cannot collect data deeper than 5 meters. So actually the information from more or less 5-10 meters in terms of geospatial data set are really poor in the coral environment, in the tropical coral environment. And so that's why I want to stress the importance of using also acoustic system. And this is not only important to map the mesophotic zone that is recently gained a lot of attention by scientists. I will not go into explain why is important from an ecobiological point of view. I just want to stress out that we do not know actually anything regarding what I call the mesophotic reefscape, which are the morphological attribute of this kind of interesting environment. Indeed, there is a paper from Laverick that resumed the work published before 2018, the mesophotic reef. And sorry, I have to move a window. And as you can see, okay, they have been published. The attention to the mesophotic reef increased recently. But if you look here, this is a schematic representation of the thematic that are basically taken into account within the paper that he analyzed. And so we have ecology, disturbances, trophic relationships, symbiosis, reproduction, so all bioecological aspects. And not a lot of information regarding the geomorphologies of this landscape. I did a very quick research on Scopus, and I found out putting mesophotic and geomorphology only 29 documents. And as you can see from the picture, people started to publish information regarding the geomorphology of the area since 2010, so very, very recently. And this situation is actually, this is at the end, the first point that I want to stress out. This missing information of the deeper part is actually, it's to me, I think that has contributed to have still a very generic classification of coral reef landforms and landscape. Many textbooks are still reporting these, maybe I think too traditional geomorphological classification in fringing reef, barrier reef, and atoll. But when you start to study them in detail, many scientists realize that it's actually not so easy to put a reef sometimes in an atoll or a fringing reef or a barrier reef. There are many situations between them, even if it was important, because this is the result of the first study from Darwin, and from which we realize that it is a very dynamic environment, and it is subject to a very, sometimes even long-term evolution that explain many of the changes we had in our planet. We have to work on determine a more precise relationship, I would say, between the processes and the landforms. And we are really missing the deeper part. So let's say what we did in the Maldives. The Maldives is an archipelago that is formed by a double chain of coral atoll reefs. As you can see from the picture, there is this double chain of atoll. It is the Maldives extend for 868 kilometers from north to south, and it includes the archipelago includes more than 1,200 coral islands distributed on the rim of the atolls and within in the lagoon system encircled by the rim. And globally, we have 27 atolls in total. And let's see a very schematic section of the stratigraphy of the Maldives. We do not actually have a lot of data in the Maldives, also from this point of view. They did some IODP drill, but still research, many geologists in particular have triggered some debates regarding the origin of the Maldives. But what is clear to everyone, however, is that there's an acoustic basement over which the coral started to grow more or less 55 million years ago. And so the basement is something like 3,000 meters deep now. So we have 3 kilometers, 3,000 meters of limestone, of corals, of carbonate rocks. And this is why one of the first book that has been published in a great literature called the Maldives Montagne di Corallo, that means coral mountains. We really have mountains on the seafloor that are including a record of 3,000 meters. So it's something that deserves to be studied because they recorded a long history actually in the Indian Ocean. And studies are very few. But let's stay in a shorter time scale and have a look at the atoll. The same authors of this divulgative book, Charapik and Passeri, published for the first time a sort of classification of the reefs that are typifying the rim of the coral atolls. And as you can see, they have different shapes. Here we have the true picture. They have different names, especially in the Maldives, because Maldivian people name them in some way. And why we have this situation? They are not randomly distributed. There is a reason, and in particular is the feedback that they are experienced with the oceanographic pattern. Because if you look at the distribution of this double chain, in the northern part you have atolls that are very highly fragmented, formed by different small reefs, while in the south you have atolls that are formed by quite almost interrupted reef. There is, in this case, there is only one pass. Pass is the interruption that allow the exchange from the lagoon with the ocean, the water exchange from the lagoon with the ocean. And why? Why? Because simply, if you look at this picture, the single atoll must basically face the ocean alone. And so it has to be stronger, definitely. And so the reef must be more massive, more continuous. While here, if you look at this other picture, for example, you will see it very well. When the rim is facing the ocean, it includes a longer reef and continuous reef. When the rim is facing the inner sea, it is characterized by fragmented reefs. This is because the energy of the inner reef is less than the one of the ocean, and so the reef can actually be fragmented. And this is helpful for the entire atoll because the exchange between water and the lagoon, the water exchange, between the lagoon and the ocean is improved, and this is something that can allow a better growth of the corals and a better resilience, for example, when temperature increase in the lagoon. So there is this very strong dynamic interaction in the coral atoll in the Maldives with the oceanographic patterns. And we started to explore this atoll, starting still from satellite data, as all the people usually do. We studied the Maldives starting from the Fafu Atoll, because there we have a center, an outpost of our university. And yes, the first approach was to collect satellite image from them. As many people did, we provided our first geomorphological map of the atoll. But we started also to apply the other techniques, because this map, this interpretation map that are provided and are easily also accessible on the web platform are missing the elevation data. That is the crucial information for having a morphometric characterization of the landforms. And now you can actually use satellite data to derive bathymetry, especially in the shallow region, which is the one that is reached by the electromagnetic waves. So we collected, or we were able to obtain this shallow water bathymetry in using satellite derived bathymetry algorithms. And now I want to show you also how we improve the resolution of our information, especially where we have the center here on this is the Magudu Reef, because this is the island that is called Magudu, and this is the reef on which this island has been established from since the Holocene. And this is the result from the satellite-derived bathymetry, but we also started to collect data with aerial vehicles. And this is the coverage we provided. That has an extremely higher resolution than the one provided by satellite, as you can see. And the most important point is that from drone imagery, you can actually apply photogrammetric techniques and obtaining 3D models. 3D models with the visible information, which is a very nice goal. This is just a picture that is showing the reflect. It's still a challenging practice because you have to calibrate and you have to collect a lot of ground truthing information to calibrate the bathymetric value and the elevation in the altitude. But you can actually obtain very nice data, and the spatial resolution can reach a sub-centimeter scale. Why is important? Because as you can see, this is the appreciation of the reef you have when you are on the site. If you want to study changes in response of the environmental changes that the system is experiencing, you need this kind of resolution. And this helps then to extrapolate the information that you can collect over a smaller area to the wider area of the satellite data. And this is just an example of a study that we carried out offshore Maldives. We provided the orthomosaic from the drone data. We apply the object-based image analysis, the kind of algorithm that I mentioned before, derived from first application on satellite data. And we were able to classify substrate in two main different types, basically, because we were focused on determining the changes in the coral coverage, in the hard coral coverage. And we actually recorded, after a very important bleaching event, a loss in the hard coral coverage. Here you can see the result from 2017 to 2018. And also, as I was saying before, you can provide a DTM and so obtain a shaded relief that show the loss in the structural complexity, which is directly correlated to the biodiversity of the reefs. But let's have a final look at what we collected with the multi-beam data. And this is very intriguing, actually. I hope I still have time. Yes. And okay, so this is this area that we surveyed around our Magodu Reef with a multi-beam system. And as you can see, it's not something like that. This is the image you can obtain with the satellite. And this is the knowledge, basically, of all the scientists regarding coral reefs. We always think or talk to coral reefs as something like that, without taking care so much of the deeper part. But if you explore, for example, the internal lagoon, as we did, you start to find very nice information, and especially you start to find the signature of this very important relationship that this, in this case, for example, for the Maldivian atolls, there's with the oceanographic pattern. Let's just see some of the information we collected. So I'm sorry, I forgot to put the bathymetric scale. Basically, the internal lagoon in the Magodu Reef is more or less around, you have the inner reef here that goes down to 50 meters in average, around between 40, 50, and then 60 meters in the very center of the lagoonal system. And I want just to comment some of the landforms that we mapped. We mapped this important sandbar in this very close to the pass. So this is a very highly energetic environment. And the point of mapping a bar is clearly an indication of a very important sediment transport in the lagoon. And all these dots here and here are all patch reef. We explored them with the ROV because we had to interpret the data with visual information, as I said before, and they are all basically patch reef. They are formed by corals, by living corals. But the top of this reef is at between 7-10 meters of water depth, so you cannot map them with with the satellite data. From the satellite data, you cannot see anything here. But we discovered a very large amount of this patch reef, deep patch reef in the lagoon. And you can see that they are mostly distributed where the arms, basically the cuspid of the reef, is kind of protecting them from the important sediment transport that is documented by this drift here. And let's have a look. So here, sorry, this is just some details of the patch reef, the Mande reef. And this is something that looks quite not interesting, I would say, or complicated, complex topography with escarpments, small ridges. But as the first time I saw it, I couldn't understand very well what is that. But then looking at the typical morphological feature that can be found in the lagoon, in the coral reef system, I couldn't notice the similarity with this kind of the scientists call it self-organization growing pattern, with this kind of special pattern that some reefs show in the lagoon. So in the lagoon, basically, you can find patch reef in mounded forms, more or less, where there are nucleus from which the patch reefs start to grow. But in some cases, you can also find this kind of special pattern. But in the presently, when you find this kind of situation, basically the reefs is alive and the corals are living here. And it seems some authors also are trying to correlate the point that you have patch reef with the kind of species that you have, the point of having patch reef or this kind of reticulate pattern. And actually, when I look here, I see something similar. But obviously now this is not the present day situation. It really looked to me like this is another image that I took from Black Whale and Hamlin. They call this kind of pattern as self-generated morphology in lagoon reef. And they were the first scientists that tried to figure out if there's a correlation between the kind of species that are able to provide this morphological partner, or if it is random, or if it is controlled by oceanographic pattern, and so on. So there's a huge debate. But the point is that when they are active, they are at the surface, they are reaching the surface. In this case, honestly, I see some similarity. Obviously, I'm not sure. We need to collect samples, but it can be a sort of inherited morphology, and it can basically provide us some very critical information if we will be able to collect sediments and stratigraphy in this environment to understand the recent evolution of the lagoonal system. As you can see here, there's an increase in the depth from the mound, from the patch reef partner to the reticulate partner. And so that's why this is one of the things on which we will focus our study in the future, to understand if understanding the special partner of the distribution of this morphology is basically associated to the recent evolution, to the late Pleistocene and Holocene evolution of the lagoon system. And yes, okay, so this is my previous comment. And finally, we also mapped some strange pattern depression offshore here in the deeper part. I know that some people here in the audience, like me, at the beginning I thought that they are pockmark, and they look like pockmark, but in coral reef system they also can be bioturbation provided by fishes. There are fishes that used to do. The point is that they are quite deep, and usually the fishes do depression that are 10, 20 centimeter deep. These are something more. And so we have to go also in detail with these morphologies. Then we can move very quickly to the outer slope. We map the outer slope, and obviously, as always on coral reef system, you can map different terraces. Terraces are important because basically mark a previous sea level change. So this is another very interesting area we have to from which we have to collect data to understand if we can correlate terraces with previous sea level position and having a reconstruction of the recent evolution of the atoll. There are very few papers also regarding this topic in the Maldives. Only 2 papers were published regarding the interpretation of the reef terraces, and no one of them date the samples. So no one collect the samples. Only they correlate the depth of the terraces to the sea level course, but still we do not have indication regarding the correlation between age and the mapped terraces. And then I finished the presentation with the most fascinating things that we saw in this environment, because even on the outer slope, we collected visual data. And I know that many of you maybe are wondering if there are the kind of mesophotic reefs that are famous in the literature and important from their ecobiological significance. And indeed, yes, this is a track that we explored in the outer slope, and yes, we map many of them. Sorry, there were other pictures, but I forgot. The animation didn't work. But however, we found many different environments and different habitats dominated by different kinds of species, but also, as in this case, some huge part of the slope colonized by scleractinians in the deep. This picture was taken at 40-50 meters of water depth. So we integrated all the data. We collected this sort of multi-source geospatial data set. Our first goal was to provide a seamless model And I think I'm quite happy with that because we succeed in doing that, but now we have to collect a lot of sample. But the point is that without this sort of general map or detailed map that is including many information in terms of resolution and kind of landforms situation in which you are, you actually cannot plan proper sampling. If I sample the lagoon, I do not know if I am on the ridge of a paleo lagoonal reef or if I am close to the inherited morphology or I mean, the point is that even in this environment now it's time to go deeper and we have technologies to do that. And oh, sorry, there was also the geomorphological map, obviously, but I want to finish stressing out still that all of that was important to provide strategic sampling and dating in the area. So now what actually? We have, the point was that we collected this nice geospatial data set, but now we have a lot of work to do because we discovered many landforms and we realized that it's very important to understand the entire evolution of the coral reef system to collect also data in the deeper region. And finally, I want to thank obviously all of you that listen to me and Luca Fallati and Andrea Giulia Varsi that are working with me, and they are basically the people that are working on the data providing me these kind of nice images. I finished.
Thank you, Alessandra. So we have time for a few
I
questions.
cannot hear you very well, actually.
Hello. Can you hear me?
Yes?
Yes.
There's a little bit noise.
Okay.
Okay.
Is there any question?
Ciao Alessandra, I'm Caterina Morigi from Pisa University.
Ciao, Caterina.
Ciao. I have a question about the patch reef. You say that they are confined in the protected area. Do you have an idea or a hypothesis why they are there? Is about velocity of the current, turbidity? What is?
You are meaning here, no?
Yes, it's very small. Yeah, one moment, because it's very small, the slide.
Okay. No, yes, I was thinking when I saw actually these are all speculations. Sorry about that, because we do not have the samples, no? Yeah. And the most important information that we need to collect is putting some current meters and determine the dynamic of the oceanographic pattern that is really controlling a lot of things here. Yeah. Because what I see from the seafloor, because anything, in any case, landforms are connected to processes, no? So what I see here is this sedimentary bar. And so there's an active transport. It looks like a sort of small drift, no? A sort of big dune. And it means that there are sediment here. If you have an input in seafloor input of sediment, the corals is not really happy, no? It cannot grow very well. And the point that the sandbar is aligned along the same limit that determine the extension of the patch reef suggested me that maybe it's because of that. So that's an active sediment transport within the lagoon in some way, especially close to the pass. And the distribution of the patch reef is determined by the dynamic, the small scale dynamic in addition, because they are not actually randomly, this distribution, the spatial pattern can be determined only if you have a very high resolution data. So this was my idea. I don't know if I answer.
Yes, you answer. But so you plan to have a cruise or a campaign to take oceanographic
Yes, we are
data?
looking for funding.
Okay.
Because we need facilities. But yes, we will be there. So Andy and my colleagues are planning a field campaign in February, next month, to collect other multi-beam data. Then we have to go there in November, and likely with the autonomous underwater vehicle. And we are planning to provide also a gravity core. yes, that can be managed in scuba diver by scuba diver, but I do not know if we will reach this depth because here we are talking about 50 meters. So we need a vessel and it's not easy.
Thank you.
Hi, Alessandra. That's Karen. We met before, I guess.
Oh, Karen.
And I was wondering whether you can say us something about the health of the reef in Magudu at this time. Did you see any changes in the health of the reef starting from when you first were in the Maldives and now? Thank you.
Well, honestly, what I have to say is that I saw many changes. In some cases, I saw them very unhealthy and covered by mucilagine. I don't know the name in English, maybe. Not really a lot of, a big part of the reef totally dead and brown because they experience a big bleaching event. But what I also realize is that they are extremely resilient. I don't know, they are strong because when the conditions are still good, they are really there to grow again. So the point of our impact, I guess, is that if we continue to impact, if we maintain a high frequency in the stresses that we are providing in the environment, so they are more or less, the fate is to not disappear, maybe, but have a very high level of unhealthy. But if the condition do not, or if in some cases the conditions are getting better, they are very quick in recovering. And you see a lot of small corals there around. Then biologists also are studying the eDNA to understand if only some species are able to recover, but other not. And so maybe there's, in any case, a decrease in the biodiversity, no? If only some species are able to recover after the bleaching event. But here in the Maldives, I saw a couple of bleaching events, very strong, that destroyed more or less everything. But then you go there after a couple of years and corals are still there. And in some cases, the same dead coral, it's not easy. You have to map them very closely, and it's a very dynamic environment. You can find out very huge changes. But I'm not the right person maybe I know that they are stressed, for sure, because every year or 2 years they are experiencing something. And they are also facing some diseases, because there are people that are studying diseases in corals, and it seems that higher temperature are correlated with a high rate of disease. So it's a vulnerable environment, but also strong.
Thank you so much,
You're
Alessandra.
welcome. Thank you to you.
Bye.
I really wish to be there. Bye.
So our next presentation is a pre-recorded presentation. So if you have questions, please ask the presenter by email.
Hello everyone, welcome to my presentation. I'm Tan Hua Ni from the Earth Observatory of Singapore. Today, I would like to talk about the glacial isostatic adjustment, which is also known as GIA, modeling of the mid-Holocene sea level high stand in Singapore and Southeast Asia. Here are my co-authors and collaborators in this project. On the right, you may see my colleague, Timothy Shaw, is surveying the elevation of fossil oyster along the coastal caves in Southeast Asia. These fossil oysters can give you the indication of the past sea levels. When you do a survey for modern oyster of the same species, you can establish an indicative meaning and indicative range for the oyster. And then for the fossil oyster, we'll do a modern analog. Assume they are following the same indicative range, and then you can know the elevation and date them, know the age. And then you can get an idea of sea level change history in Southeast Asia. So first, what is mid-Holocene sea level high stand, and why do we have a high stand? As you may know, the high stand is because of the GIA, which describes the dynamic interaction between the large ice sheet surrounding the Earth and the ocean, and causes sea level variation since the last interglacial. So if we go back to the last glacial maximum, since then, the large ice sheet will melt, and in the near future, the surface will rebound, and outside the ice margin, the full bulge will subside and collapse. And these subsidence will cause a void, which accommodates the water transformed from far field, causes level 4 in the far field region. This process called equatorial ocean settling. On the other hand, in the far field continent, like Southeast Asia, when you have a very shallow continental shelf, due to sea level rise, the seawater will depress the seafloor, and the seafloor will subside offshore and uplift onshore, which will also cause the sea level fall since the mid-Holocene. Both equatorial ocean settling and continental leveling will cause a sea level high stand during the mid-Holocene time period, which is around 4,000 to 7,000 years before present. In Southeast Asia, we standardized the published sea level data. Here we created a peak high stand database. When we say peak high stand, which means in nearby region, we only choose the data that gives you the highest high stand, which is the positive R's relative sea level. And then we follow the Halsey template, standardize all the data. We have 16 data in this program. And then they can be compared with each other and also can be compared with the GIA model to validate the GIA model predictions. For the model, we both consider 1D and 3D GIA models, which are laterally homogeneous and laterally heterogeneous GIA models. As you may know, for the GIA model, they have two parts. The first, the Earth model, which includes the density, elastic properties, and most importantly, viscosity. And the ice model, such as the I6G NC model, developed from the University of Toronto group. The ice history model describes the ice coverage and thickness distribution evolution history. Unlike the traditional spectral normal model method, which can only simulate the 1D laterally homogeneous model, we use the finite element model, which means you can define the Earth properties at each element separately. So we can simulate the laterally heterogeneous, the so-called 3D GIA model. To solve the sea level equation, we also consider the rotational feedback of ocean and ice load. So we have all the outputs listed here. First, sea levels, also the surface motion, including both horizontal and vertical, gravity field change, Earth rotation, as well as the GIA stress evolution. For the 3D viscosity structure, there are two parts. The first is the background 1D viscosity, plus the lateral viscosity perturbation. The lateral viscosity perturbation is derived from the scaling relationship reviewed from the microphysics in high temperature, high pressure environment. Here, this term, the delta Vs divided by Vs, is the lateral shear velocity anomaly, which we take from the global seismological model. Here you may see the beta, which is the scaling factor, controls the contribution of thermal effect to lateral viscosity variation, which is also the magnitude of lateral heterogeneity. Here's an example of the high stand at Singapore. You see all these gray boxes are the sea level index points. Has been standardized in chart at 2021 in Horizon policy in the publication. And then we take the I6GC VM5A as the reference model. For the rest, all the curves, they only change one certain parameter from the reference model. You may see from the reference model, although it shows significant misfit with the data, the misfit decrease with time when they reach mid-Holocene, intersect at about 6,000 years before present, and then decrease linearly to present. The data shows are lower than present, but the model cannot capture that feature. And we change the Earth model. First, we try to incorporate 3D upper mantle and lower mantle, as shown in orange solid and dashed line. You see, for the 3D upper mantle, they should only change very slightly compared with the reference model. However, if we consider the 3D lower mantle, you see the prediction curve will be leveled up, and the peak height stand will increase by 2 meters, reach 5 meters. And it will decrease the upper mantle to 1 times 10^20 Pascal. And also, we tried increase the lower mantle to 2 times 10^22 Pascal. You may see here, the blue solid line and blue dashed line, they differ a lot from the reference model. We also tried to delay or shift the melting history for Antarctica only or globally. You see here the two sine curves, solid and black dash. You may see they have a very important feature is the peak height stand timing. When we only change the Earth model, either 1D or 3D, the timing doesn't change. However, when we change the ice model for 1 Ka delay, you see the peak height stand also delayed by 1,000 years. Then we try to study the high stand magnitude, their sensitivity to the lithospheric thickness change, upper mantle and lower mantle viscosity change. So, as you see on figure B, the high stand magnitude, which is the maximum of the high stand, is insensitive to the lithospheric thickness change. That's because the high stand is mainly caused by equatorial ocean sampling and continental nivering. For the change of the lithospheric thickness, the two processes will compensate each other, and so it doesn't change too much. For the upper mantle, we see with the decrease of the upper mantle, the high stand magnitude decrease notably, especially when they reach 10^19 Pascal. The high stand disappeared. There's no more high stand because at such a low viscosity, the relaxation time will be very short. And then during the middle to late Holocene, the equilibrium has been reached, so there's no time for the accumulation of the high stand. For the lower mantle viscosity change, when the viscosity is lower than 10^22 Pascal, you see, similar to the upper mantle, you see very obvious variation. However, when they over 10^22 Pascal, they only decrease slightly with the viscosity increase in a lower mantle. So next, let's see the spatial evolution with time. So here shows you the high stand in Southeast Asia since 9,000 years before present until 1.5 thousand years before present at H. So you may notice from B, which is 8.5 kbp, the high stand first emerged in the center of Malacca Strait and southwest Borneo in a magnitude of 0.5 meter or 1 meter. And then the high stand, which is the red positive relative sea level, expand to cover almost all the standard land and reach the maximum at D, figure D, 6.5 kbp. And then since then, the pattern is consistent, but the magnitude decrease. Next, let's look at the peak high stand timing at 6.5 kbp. You see the dashed line here shows you the boundary for the standard land. It's almost overlap and consistent with the boundary of the high stand, which is the zero line. Here you see the difference between the red and blue. and the peak high sand around the Malacca Strait and also the east coast of Sumatra can reach 4.5 meter. And the larger area over 3.5, including southwest Borneo and northern coast of Gulf of Thailand. Next, let's see how this spatial change because of the change of the 1D upper mantle and 1D lower mantle viscosity. So for the high sand sensitivity in the figure A shows you when we decrease the upper mantle viscosity to 10 to the power 20 Pascal. You see, they can decrease by over 2 meters in the center of Malacca Strait. And for the South China Sea and also in the ocean, they show positive sensitivity. And here the black line, solid line, and the black dashed line, which indicates 1.25 meter threshold values, which is roughly the average uncertainty of the proxy sea level data in Southeast Asia during the mid-Holocene time period. On the figure B, which is the sensitivity to the lower mantle viscosity, you see they show positive sensitivity centered around the east coast of Malacca Peninsula, over 1.5 or 2 meters. And almost all the inner Thunderland, the sensitivity are over 1.25 meters, which can be resolved by the proxy sea level data. Here shows you the sensitivity of 3D upper mantle and lower mantle. They have similar pattern, but with different magnitude. For the 3D upper mantle, only like 0.5 or 75 meter, but for the 3D lower mantle, they can reach 1.75 in the center, east coast of Malacca Peninsula and West Borneo. Notice the sensitivity of 3D viscosity is also will be influenced by the topographic model you choose, because the 3D structure are constrained by the seismic topographic model. If you choose different seismic topographic model, you may get slightly different results. Here shows you the high sensitivity to the melting history shift. So if we shift the Antarctica ice sheet and the global ice equivalence level by 1,000 years, you see they both near to negative sensitivity, similar pattern but different magnitude. That's because at 6.5, the peak high sand timing, only half of the ice equivalence level contribution are from Antarctica. So here comes to the key output of the paper, the high sand treasure map. Because in Southeast Asia, although we have lots of the publications shows they have the data, but the data are widely spread and uneven. Also, the data quality are different. So we try to identify some key location that can provide the important constraint for the model. So the first question is, where should we go to find all these the potential high sand records? So here we try to identify the region that have the high sand record, which were previously flooded by the sea level, which means that previously they were below this level, but now they sit above this level. So we try to identify the region R here, which indicate the region that potentially have the sea level record. Compared with for the Peniel topography, we can derive from the present topography and our sea level prediction. The present day we use GEPCO 2022 rig, and then we should derive the Peniel topography change. And then if we combine or integrate the region through the whole Holocene time period, then we can get the region that they have the high sand record within the Holocene time period, which mainly the mid-Holocene time period. And these are the key areas that to preserve the evidence of the mid-Holocene high sand, which are the key area for the future sea level collection efforts. So here is the key figure in the paper, the high sand treasure map. You see all the red dots indicate the location that should have the high sand preservation at different magnitude. You see here with different color. Mainly the red means they have over 1 meter of the magnitude of the high sand. And all the purple dots indicate the published and our standardized sedimentary materials that review the high sand record. The green, which are the fixed biological indicators, the coral, the oyster materials, see there were high sands. You see, most of the purple and the green dots, they somehow overlap with our red dots, which means they validate our map. It's valid we see there should have some high-stand or the past publications said that already. Which means in the future, like for the along the Malacca Strait, east of Sumatra's coast, northern Java, southwest Borneo should be the key area for future sea level collection efforts. However, we also noticed for the Mekong River Delta and the Bangkok, they should have a various of the high-stand record. However, we don't see much in the previous publication. We suspect it's mainly because this region, they have very low line elevation, and also they suffer from the subsidence and coastal erosion. So all the sedimentary materials has been eroded or washed away. They are not in situ. However, for this region, if you find some the mid to late Holocene proxy records, when you do a comparison with the model, you can see the difference, and that can partly can reveal the vertical land motion signal, like subsidence signal. Also, you may notice the blue dot here from Kelsey et al. 2015, where they reconstructed sea level history from early Holocene until the late Holocene. They didn't see the high-stand, and our data is consistent with their results. So here we compare the high-stand magnitude. You see all the blue indicates the J prediction, and the red indicates the data, including slips and marine and tertiary Newton data, which prove the lower and upper bound of the positive level. You see, they are all consistent apart from the Chao-Ferreira delta data, which show a mistake. We suspect the data itself has some unknown local influences, as it's too high, over 7 meters, and for the rest, don't reach that high. So in summary, our results show that the Earth model variation only affects high-stand magnitude unless extraordinarily low upper mantle viscosity is used, like lower than 4 times 10 to the power 19 Pascal, which leads to a shift of the timing of the high-stand towards present, and the absence of the high-stand when the upper mantle viscosity is lower than 10 to the power 19 Pascal. And we also see the magnitude of the high-stand is sensitive to the upper mantle viscosity and lower mantle viscosity variation, especially when the lower mantle viscosity is lower than 10 to the power 22 Pascal. However, the mid-Holocene high-stand magnitude is relatively insensitive to the lithospheric thickness variation. And we see the ice model variation can change both the timing and the magnitude of the high-stand. If we delay the ice melting history, the high-stand timing will be later with the lower magnitude of the high-stand. We review that the Malay Peninsula, east coast of Sumatra, northern coast of Java, and southwest coast of Borneo are very likely, which means more than 90% of probability to have the mid-Holocene high-stand preservation. Here's the paper. If you want more details, you can refer to the paper. You can also send me an email for further details. Thank you.
So thank you. Our next presentation is Mark Furtz from University Center in Svalbard.
Okay, can you hear me? Yes, closer to my mouth. There we are. Thank you very much. We've had some really nice talks from the tropical realm, which obviously is what this meeting's about, but I thought I would drop an ice cube in here in the proceedings just to cool things down a bit. This is work that it's been ongoing in my group in Svalbard for the past 4 or 5 years, and really represents for me a return to my interests as an undergraduate when I did a project looking at past interglacial shorelines in the southwest of England, and stems from the work we've been doing reconstructing actually Holocene sea levels around Svalbard, coming across some kind of inconsistencies in the record which were very, very hard to explain. But I will try my best today. Let's see if we can advance. Yes. Just to kind of set the scene, really this is about shorelines in high latitude environments during the last interglacial period. No, we call it the last interglacial. Perhaps the penultimate interglacial is a more accurate term, seeing we are in interglacial anyway. We're talking about the period about 130 to about 115,000 years before present, probably peaking about 125,000 years KBP. Variously called the Eemian in the European kind of nomenclature, Sangamonian in North America, Ipswichian in the kind of British Isles, Valdivian in Chile, MAS 5E. So there's a lot of interchangeable names for the last interglacial. Primarily I'll be using the term Eemian because we're referring to the Svalbard record here. During that period, eustatic sea levels were about 6 to 9 meters or so higher than present. Now, of course, there's no such thing as an observable eustatic sea level because there's so many locally contributing factors to your relative sea level at any one point in time. So it kind of varies from where you are, but when we look at, what have I done? What have I done? Done something bad. Okay, it's back. Okay. How do I get the laser pointer here? Which button do you know? Okay, no worries. Oh, I can just gesticulate. When we look at the record though from tectonically stable settings, you can see that it does vary between about those kind of values of maybe perhaps in some places kind of 6 meters. No, it switches it off. No, to 9 meters. But we need a tectonically stable setting to be able to observe something approaching that. As we have, at the time during the last interglacial, our air temperatures, especially in polar latitudes, are significantly higher than present. 2 to 4 degrees C greater than present. And that means that we have much more limited ice masses. So that those higher sea levels can't be accommodated simply by the thermal expansion of the oceans alone in that period. We need reduced ice masses, more water back in the oceans. So we see, for instance, the Greenland ice sheet is more reduced, and the West Antarctic ice sheet is suggested to have been collapsed at that time as well. In contrast to the Holocene, sea levels during MIS 5E and global temperature was far more unstable. So we see pronounced changes throughout that interglacial of sea levels, as well as the high stand around about 125,000. So there's just some kind of modeled reconstructions of the Greenland ice sheet showing significant reduction compared to present day based on a range of different authors. And also the consequences for low-lying areas where, for instance, Scandinavia through the what became the Karelian Seaway is actually an isolated island from Europe rather than connected to mainland Europe. So significant kind of changes in paleogeography during that interval as well. How are those sea levels expressed geologically, geomorphically in the record? It's actually quite hard to pin down what the shoreline actually is. It's not an easy job. We think, oh, we just find an old beach, that's your shoreline. But it depends on its preservation. It depends on how we define geomorphically the different parts of that preserved beach system and how they relate to past sea level, where you've got a range of different tidal ranges. Are we looking at what is your mean sea level? What is your mean high water mark? These range of different parameters that we're trying to reconstruct. And that will vary from one site to the next and from one author to the next. But depending, I'm sorry it's a bit fuzzy here, but depending on what the system we're looking at, it's going to express very differently. When we're looking at ancient lagoonal systems, we're looking at rocky shore platforms, where we're looking at kind of beach rock or coral reef terraces that we've kind of touched on a bit already. It will really depend on the system, the depositional erosional system, and the surrounding bedrock, what the expression of those former sea levels is. So So it does take a lot to kind of figure that out. In terms of its expression around the world, you can see from this figure here that a lot of the sites recording higher sea levels during the last interglacial are in the tropics, but there are many that are in kind of mid-latitudes that really concentrate around population centers. So this map is a function of preservation, yes, but also of research activity. So we see a great concentration of sites around the Mediterranean, around Northwest Europe, on the Californian coast, in Southeast Asia. And although that sea level was, kind of 3 maybe to 9 meters above present, it's overprinted significantly by tectonism. If we look at this transect from along the west coast of South America, over about 5,000 kilometers, heading northwards to the right, you can see how that stage 5E shoreline varies considerably because of tectonism along that active plate boundary along that coast. And if we go to somewhere that many of you may be familiar with here, the Ossa Peninsula, while I was there last week, I was looking for the last interglacial shoreline, that's hiking and flying over that area, and I couldn't see it initially because I was looking too low. I was used to seeing it around about, 5 meters or so, but in some cases it's up over 60, 100 meters because of the ongoing tectonic uplift that has elevated that former shoreline. In other places, if we look around the European margin, we can see that those preserved shorelines are really south of the limit of the most recent glaciation. Okay? So these are in unglaciated areas where we have that preserved. And in that case, you can see in this figure here, we typically have the rock platform. We've got beach sediments, many cases that they are cemented by manganese, and then we have kind of solifluction, kind of periglacial deposits over the top, forming these kind of coastal terraces with the active cliff at that figure on the left, and the kind of paleo cliff preserved behind. What becomes interesting, though, is especially when we start thinking about the last interglacial, is that it's a really important partial analog for future warming. And therefore, looking at this in formerly glaciated high latitude environments is really important. If we wanted to reconstruct how those areas are going to respond to climate change, how the ecosystem that could be preserved in fossils associated have responded to that. But there are exceedingly few records of these 5E coastlines preserved in glaciated or formerly glaciated areas, for obvious reasons. Ice sheets eroding or overprinting, depositing, and burying those features. A very blurry example here on the left is one from northern England, where we have a very subtle escarpment along the coast of Yorkshire and Lincolnshire that is kind of buried in till but represents the old coastline. The right-hand figure is just a kind of schematic from maritime Canada, again showing in a coastal section where erosion has exposed the old rock bench. There's marine and shore sediments along the base and quite extensive tills on top. But it has no geomorphic expression. It's completely buried. So these are few and far between at high latitudes. There is a recent record that's actually just been published this month by Ekaterina Taldinkova, and then it includes forams and ostracods in those sediments from the White Sea area. That's a really quite exciting paper that's just come out a week or so ago. But again, that doesn't show any evidence of glaciation over the top, just extensive sediments that record that kind of seaway between the Baltic and the White Sea during stage 5E. So what about Svalbard then? We do have in Svalbard, if we introduce those, some of you are familiar, some of you aren't. Svalbard is this group of islands halfway between Norway and the North Pole. It's Norwegian territory. 5 major islands, hundreds of small islands, 74 to 81 degrees north. It's still extensively glaciated, over 60% ice cover. But during the last glacial maximum, it was fully glaciated. Okay, so it's part of the Svalbard Barents ice sheet. So it's part of that big kind of complex of ice sheets that extends all the way from the British Irish, Fennoscandian, Svalbard Barents, right up that margin. And we see quite significant isostatic depression associated with that. So that would be our reconstruction from the dated 1 project with Svalbard up there kind of towards the top center as part of that ice sheet complex. With our glacial-isostatic depression and rebound, it means that our shorelines dating from the earliest Holocene, for instance, are anywhere between 45 to over 100 meters above present. So there's a strong history of ice depression and isostatic rebound in that area as well. So rather than thinking of our last interglacial shoreline as we would here as being a sea level high stand, here our last interglacial shoreline is our sea level low stand. So we have that inverse kind of pattern. We do have some sites in Svalbard that have been previously recorded as containing these MIS5E last interglacial deposits. Quite remarkably, given the amount of glacial erosion that has gone on in that setting. Really dated from amino acids and luminescence dating, perhaps more solidly, and mostly as raised marine sediments, typically sandwiched between glacial deposits, recording glacier marine kind of near-shore environments. A lot of the work that Helena Alexanderson has done, for instance, showing that. Here's another good example of that. We've got a recent paper giving you an example. Again, back to your foraminiferal faunas, with your Eemian kind of faunas here, typifying really quite characteristic kind of fjord settings, perhaps in some cases suggesting slightly warmer conditions than present. Another example here showing very similar Eemian sequences, MIS5 sequences down the bottom. But it's not just the microfossils, also megafauna preserved in there. We even have early polar bear mandibles preserved in these Eemian deposits, which have been really important for understanding the evolution of polar bears during this time and the importance of island archipelagos as a refuge for them during interglacials. But the work that we're doing this is kind of an introduction to kind of new work that started on this peninsula here. This is Erdenfleur in Isfjorden. This is about 100 kilometer long, 60 kilometer wide inlet on the west coast of Svalbard. And what we noticed midway through the Holocene sequence of emergence is a prominent cliff line. This has been attributed to a mid-Holocene transgression, but some of our more recent radiocarbon dates that say this transgression didn't happen. We have whale bones that should be not a beach at the time. It's hard to get a whale to walk inland to die. So we're kind of overturning that idea. The problem then is that we don't have enough time during emergence in the Holocene to cut these cliffs. These have to be old relic features that are being re-emerged and trimmed as sea level falls. In fact, when we map them, we see we have over 100 kilometers of these cliffs, about 5 to 8 to 10 meters above modern sea level, cut in bedrock. You can see their morphology here. So here's another one. There's the modern cliff. There's this backing cliff. They all occur below the marine limits. So they have been underwater. They have been glaciated. And then they've emerged. So our project is to actually explore these cliffs. It's just started, this project, to look at their elevation, map their distribution, and if we can then project that to see what de-leveling of this surface has taken place, to reconstruct the nuances of isostatic rebound, but in particular ongoing tectonics in the archipelago. That means doing a lot of digging to try to find sediments preserved at their base, to maybe run GPR radar across them, as in the title picture, and then look at the preserved floras and faunas, hopefully at the base of those cliffs if we can find them. And of course then we've got dating, so we'll be talking about luminescence dating to really prove that these are from 5E. So the project has really just started. I think it's very exciting. This is the first time that these cliffs that have been described as from that period. It's just a hypothesis at the moment, but I think it's a strong one. But it does fit in with some of this existing data that we have stratigraphically. So if anybody wants to join in the project, they're more than welcome. We're trying to apply for funding at the moment. So thank you very much.
Do you have any questions? Yeah.
I have two questions. One, is this place tectonically quiet at all, unlike North America? And the second question is there suitable material for luminescence dating? Thanks.
Yeah. My question was, maybe you said it, but maybe I didn't get it. Are there like, do you know like the highest coverage during the Eemian period in the Svalbard? Thank you.
Thank you. Yes.
Summer, we're going to drill along the western Svalbard, the IODP, and it would be very nice to compare the marine and the continental.
Thank you so much. Okay.
Curiosity, your project is planned to sample on the western part or also on the eastern part of Spitsbergen? Okay. you don't know if there are exposure of the MIS5. Thank you.
Question?
Mark, just a curiosity. You said that last week you were looking for old coastlines and that you were looking too far down. And I was wondering, beside the different tectonics, of course, which are the techniques to like map old coastlines in the Arctic and in the tropics, in your opinion, very different, or are they just the same?
Thank you so much, Mark. So our next speaker is Beatriz Naranjo from University of Costa Rica.
Hello. Good afternoon. Thank you for the invitation. I'm part of the biologists here that needs to be checking the presentations, but it's been really interesting. I've learned a lot. My name is Beatriz Naranjo. I'm part of the Costa Rican team that is working with deep sea biology. And the presentation will be full of, we are going to, it's a work in progress. I want to talk about the innovations in video analysis that we have accomplished so far, but also all the work that we have ahead. I have the opportunity to work with Jorge and Odalisca and Maria and a bunch of other people. We made some expeditions, especially last year. They already talked about the Pampa Submarina. So all these video analysis that I will be speaking about is coming mainly from those couple of expeditions, but also, as Don Jorge explained, we already made some expeditions, especially in Isla del Coco National Park, across the Isla del Coco submarine ridge, La Pampa Submarina, and the Central Pacific, and also the Osa Peninsula. So we have many hundreds of hours of video that we need to analyze. I'm a marine biologist, but like facing this challenge that video and large quantities of data impose, I started to learn web development in order to improve my programming skills. It's all about the data. So right now I'm in the middle of being a biologist and being a web developer, and we have a lot of work ahead, and it's really exciting. And this is the deep sea submersible. It's a human-operated vehicle, and I put the image in black and white because I think even if the technology is getting, like a lot of improved, I think this is or right now, human-operated vehicles are really expensive, and they are mainly used for touristic purposes. We sometimes have access to that, and one example is the deep sea that was working in Isla del Coco since 2006 until a couple of years ago. They already left the island. So we have a lot of data coming from HOVs, but of course there are other technologies that are getting cheaper, more affordable. And this is one example. This is a drop camera. It was developed by National Geographic team, and it's an example of autonomous way to collect video. So this is really interesting because you can deploy these cameras from a small boats. You send them to the bottom of the ocean. You can send them to 10 kilometers if you want, and then you program them, and they come back to the surface by themselves. So I think, of course, it's like kind of obvious, but video information, it's our way to watch the deep sea. And as these technologies are getting cheaper and affordable and more accessible, I think we need to prepare to all this data that will be coming in the next years and learn how can we take as much of information as possible from all these videos. So, so far, of course, video has been really important studying the deep sea, and some examples of that are it's a really useful tool to identify species, also to conduct behavioral studies, habitat assessment. This is an example of garbage that we found in Isla del Coco, one of the most, supposed to be one of the most pristine places in the world, but still we have some human impacts there. And of course, video is a great tool to trying to improve the selectivity of the sampling. Like compare it from years ago, where all our information from the deep sea was coming from trawling, for example. Right now we have all these cameras that allow us to pick, to select specific animals, for example. Of course, all this video will allow us to monitor the environment. This is a robot that is controlled by the internet. It's always at the bottom of the ocean. We don't have that, sadly, hopefully one day. But of course, all the video that we have will be like the most obvious way to compare what we had 10 years ago from now and so on. And of course, an image, and especially video, can talk more than words. So video is an important tool to communicate all the findings that we have. You can present a list of 1,000 species to, I don't know, like decision makers. But if you don't put a good story and good images in that information, you will not have the same impact for conservation. So as I was saying, video is a powerful tool, not just to extract information from the video itself, let's say quantities or densities of organisms, but they can also like improve the conclusions you can make. You know, like for example, when you took a sample of sediment, the video and all the associated information can be really useful to inform other methods of studying the deep sea, and this will have a strong impact on the decision making for conservation. However, working with video, it's really can be really overwhelming because there's a lot of information, as I was saying. So the first time that we need to take is to improve our data literacy. That means how well we read, interpret it, and communicate all this data. Because as I was saying also, even with good data is there, if you don't have a good story to tell, the consequences might not be as good as you wanted. This is the, in the background, this is the ROV control from the Falcor 2. This is the ROV Sebastian watching octopus in this case. And just to put you an example of the amount of video that we have from last year, we had an expedition in June, and we have more than 200 hours of video from that expedition. We have almost 200 from December expedition, and you can extrapolate that to the hours of video that we need to analyze. So one of the main challenges that we have faced working with video is how we collaborate between us. And we are using this platform. It's called Tator. It's a way to annotate video. I will speak about that in a bit. But this is an open source, collaborative, web-based cloud where we are uploading all our dives. This is coming from last year's Schmid Ocean Institute expeditions. So all of us that participated in that expedition have access to the videos through this platform, and Ola and Maria love to use them. So it's really useful not just for take information from the video itself, but also you can relate the video with a lot of information that the ROV is gathering. In this case, we were collecting this fossil, whale fossil, skull. And if you see here, you see all these like lines. If you made a zoom in that, you can see that for every second of the video, you have access to all the sensors that the ROV has. For example, a CTD. You can check what was the temperature, the oxygen, the conductivity, the depth. You can check the latitude, the longitude. I mean, you can check everything in just one place. And this is pretty amazing because Schmid Ocean used our expedition as a trial for to use Tator in upcoming expeditions. And this is a really nice way to collaborate. You have a lot of analytic tools here where you can download all the observations you are making in the video. And there is a Python client and some geek stuff that you can do with this powerful tool. So in this case, for example, it's really useful for our geologist colleagues because they can, like go back to the video, see where they took the course and extract the information they need. And with this, I can also see how the sediment, for example, look when they collect a sample. And every time we used on the ship during the expedition, we used software that Schmid Ocean developed. It's called CLOG, and CLOG is a tool where you can press a button and say, like, in this moment of the dive, we collect a sample. So every time you click on that button, it makes a timestamp and relates all the associated data from the ROV with that specific event. And then when we go to Tator, we still have access to all that. So I'm not putting that here, but if I open one of these videos, I will see all the events, when a sample was collected, or we have a lot of, like anthropogenic observations or highlight something that really cool happened there. So it's been pretty amazing, even if Schmid Ocean always upload the video to YouTube, and that's a really interesting part of those expeditions that are really open to the public. So in these cases, if this doesn't exist, we have the YouTube. But from other expeditions, we don't have anything. You have to go to to the original video data and look all that information step by step. So this is a really big improvement. So I was saying, each time a sample is collected, you can also rewatch that on this Taylor platform. And what Taylor allows us, thinking in this case from a biology perspective, is that you can start to identify everything you see. In this case, we have a tripod fish. So you want to make that annotation on the video. Like in this moment, I saw a tripod fish. So one important feature that this has is that it's connected to worms. So it allows us to, don't commit errors when you are typing. And this also allows us, because each of these is connected to a AFI ID for each taxa. So if the name changes in the future, you still will have all the associated information. We are making this for biology annotations. We have one annotation card for fish and invertebrates. For example, if I want to be working with parasites, I can just download all the fish that had parasites, for example. You can put like specific comments, behavioral notes, and so on. We also have one for geology. You can specify the type of lava, mineralization, and all other geological information. And as I was saying, we are also using this to standardize our anthropogenic observations. And the goal is to put all this annotated information in this open source database. It's a database for images. And this FathomNet is basically an image database that is coming from BARS. BARS is an annotation, video annotation and reference developed by Mare. And they were putting all the, for example, this image, you can see a skate here. So annotate an image, it means that you know what is in that image. So in this case, they annotated 23,000 hours of video. It's the largest database for images in the deep sea. And they put it in this system called BARS. However, this is different. Annotate is different to make label data, because the difference between this image and this one is that in this one, there is a skate, but you don't know where. I mean, you don't have the specific information for which pixels contain skate. So in this case, we are also making the annotation, but we are specifying that in this bounding box, the blue one, you have a skate. So this is what we need to be able to analyze large amounts of hours of video. So right now, if you look in FathomNet, the Central Pacific of Central America, you see that there's not any information. So our goal is, after all this analysis, we will put all our images here. And after this, we can start thinking about machine learning to help us analyze the rest of the video. I'm putting this example here. This was our longest dive. It was more than 30 hours. That means if you want to rewatch this dive working 8 hours a day, you need 5 days to rewatch this video without doing anything else. So if you want to extract information, imagine the time that you need to work with all this. So this is why we are hoping with this to train supervised machine learning algorithm and start to say this fish is, it's Batipteroids, this coral is Paragoria, and so on, and then to have a model that will allow us to identify as much as we can. But of course, this is a common saying in computer science, garbage in, garbage out. It applies for real life as well. So no matter how good your model is, if you put garbage in the model, you will obtain garbage. So we are in that first step to put labels on our data. And after this, when the images are in the database in an organized way, we can start like using all this information to develop our own applications for science, education, decision making, and so on, through application programming interface. This is just an example of how it looks. PhantomNet has an API, or application programming interface, where you can basically say like, hey, I want to get all the images that contain a coral or so on. So you can start bringing images into your own applications for specific purposes. So next steps, we need to improve our way to how we storage the data, how we analyze it, of course, how we visualize the data, how to produce communication tools and apps, as I was saying. And one of our goals is to work on a Costa Rican deep sea repository that will contain, hopefully, all the information related with this amazing environment. So it is, muchas gracias. If you have questions, I think this is all the baseline that we have from the deep sea, so it's pretty amazing. I mean, all these videos are really valuable, and it's so really excited, and hopefully will help many researchers, not just biologists, to collaborate in this analysis. Thank you.
So thank you, Beatriz. We have time for questions, comments.
Thank you, Beatriz. Very nice presentation. And one question is, are you doing all this work by yourself?
No. We are starting. This was really nice because Schmidt Ocean is paying for all this cloud-based service. It's really expensive. So it's an important step for us because not just in video analysis, but the expeditions by itself help us to gather the people that are working in deep sea in Costa Rica. So we are in the process to start a team of annotators. And it's really nice because you can bring different backgrounds to this analysis. For some part of the work, you don't need people that know how to identify fishes. You just have to make bounding boxes around each organism. So it's an important way to bring people interest that maybe they don't have a scientific background, but they can help in the process.
Okay, thank you. And another question. I didn't really get the connection with worms. So
with
you're
worms?
You're putting all your data in worms?
Not in worms, but you use the taxonomic hierarchy that worms has to connect that information with your observations. So the good thing with this is that it's all connected because you have the OBIS. I don't know if you know, OBIS is Oceanographic Biodiversity Information System. So it's basically an open source database where you can upload all your observations, but you don't need an image for that. In this case, we will have like all the record, but also the image that is going to PhantomNet. So it's all connected at the end, and people from the other side of the world, if they want to train a machine learning algorithm, they will be able to do it because it's open. Mm-hmm.
So thank you. Another question, comment?
Thank you, Beatriz, for the presentation. It was very nice. Just a comment. Remember the pictures that I showed in my talk? All of them were extracted from Tator. That is a very important tool and very useful. And also, just to comment that we collected samples. So in the future, we will be able to match the sample with the picture and with a more accurate identification. And it has been done before without samples, just by pictures.
Mm-hmm. Yeah, and just to add, I talk about the identification of organisms because it's what I do. But of course, this video is really useful also for, like Alessandra was telling, like 3D models for the habitat assessment,
there's really a powerful tool.
Yeah, and also a comment for geology. For example, when you have the video and you see the rocks or the outcrops in the deep ocean, you don't have time to take the sample, but then you can have the time to analyze the contacts, the shape, the thickness of the beds, for example, and this is very useful. Yeah. Okay, so thank you so much. So we finish this part, but we continue with the speed talk. We have one speed talk today. So the next speaker is Stephanie Murillo from University of Costa Rica. This is the group photo.
Hello. Okay. Hi. The title of our talk is Geological Analysis of Continental and Marine Sediments in the Terra Sierpe Deltaic System. This is an ongoing project, and it's also part of an undergraduate thesis of the student named Laura Alvarado Marchena. She couldn't be here today because she's out of the country, but yeah, and in this project we're working together with Maria Sandoval, who talked yesterday. There's me, there's Max, Maximiliano Garnier, and Jorge Cortés. Okay. The location of the samples is in the south of our country, in the Peninsula Eosa, and we have, you can see the purple circles are river sediments, as well as the red, these red samples over here are river sediments, and then we have the marine sediment core samples, which were taken by the Pristine Seas expedition in 2019, and the river sample sediments were collected in 2022. So for the methodology of the project, we have the sediment collection first, obviously, then the subsampling, of course. If you remember yesterday from Maria's talk, there was a photo of one of the cores where they cut it in half, and then it's divided into segments that are approximately 3 centimeters each, and each of the 3 centimeters are sampled. And then the samples are used either for physical properties or for the mineralogic and biogenic analysis. And for physical properties, we measure unit weight, specific gravity, moisture content, particle size distribution, and compressive wave velocity. And for the mineralogy and biogenic analysis, we use smear slides, and we've done XRD, which is, sadly, we don't have a lab here in the geology department, but there's one in the chemistry school in the University of Costa Rica, and that's where we do the analysis. And, also dating on one of the samples. And one of the objectives of the project is to determine the influence of the deltaic system on the marine system and comparing both environments. And like I said before, this is still an ongoing study. It's starting, okay? So here are some preliminary results. Here are the physical properties comparing the marine sediments and the river sediments. And this is in the poster, so you can see into more detail, and I'm sure Max would be able to answer any questions about that part. And then we have the photographs of the smear slides. Here we have some photos of marine sediments, and here are river sediments. We have seen some differences in both. Here's one of the corals of Olarisca that she was talking about yesterday, but a little tiny piece. And then we have here's some minerals like blue chloride that we've seen in the marine sediments. And in the river sediments, we've seen wood, for example, in Poland. So there are some differences. But just some of the conclusions is that the physical properties are very similar for what we're seeing in both environments, which was expected. There is a marked difference in the biogenic content, and the mineralogy In both sediments, we are seeing some differences, but this is just getting started, okay? She's just starting the student is counting 300 to 400 grains in each of the smear slides, okay, and trying to compare the mineralogy, but project is starting, so yeah, that's just preliminary. And that's it, basically.
Thank you so much, Steph. So for now, we ended this for today, and we go for the coffee break. And and visit the poster, please. Yeah, of course, yes, not just the coffee. Okay, so thank you so much for being here today. Remember that we have the dinner at 7 in the República, so everyone is